Arrasaleón, buenas tardes a todos. It's a pleasure for me to introduce Theodor Hansch. Alemaniako Heidelberg hirian jaio zen. Bertan, Bunsen kimikariaren ohorez izendaturiko Bunsenstrasse kalean bizi zenez, 6 urte zituela, Bunsenek zer egin ote zuen galdetu zion bere aitari. Bere aitak Bunsen metxeroa ekarri zion etzera, eta erakutsi zion nola gatza botatzean sugarraren kolorea urdinetik horira aldatzen zen sodio atomoen kitzikapenagatik. Haren esanetan, hurrengo batean, aitak metalurgiako laborategi batera eraman zuen eta zientzialari izateko grina piztu zitzaion. Haren hitzetan, at the time when other boys dreamt about steering steam locomotives, I started to see myself as a future scientist. Jakin minez, etzean bertan kimikako esperimentuak egiten hasi zen, eta erabiltzen zituen materialekin istripua izan da gero esperimentuak egiten jarraitu zuen, baina oraingoan fisika eta elektronika arlokoak. Heidelbergeko unibertsitatean fisika ikasketak hasi zituen, segituan fenomeno fisikoak eredu simple eta intuitiboen bidez azaltzeko zaletasuna erakutsi zuen. I was awed by the power and elegance of pure mathematical reasoning, esaten du berak, but after a while I realized how much the complexity of an abstract formalism can sometimes distract from true physical insights. Since then, I've acquired the compulsion to always try and construct the simplest possible intuitive model to understand a physics phenomenon. Heidelbergoko unibertsitatean zegoela, asmatu berria zen laserraz interesatu zen, izan ere, 1979 urtean, laserrari buruzko doktoradutza bukatu zuen. Hurrengo urtean, Estatu Batuetara abiatu zen, Stanfordera, laserraren asmatzaileetako batekin lan egitera. Bertan zebilela doitasunaren aldeko grina piztu zitzaion eta optical frequency comb technique izeneko ideia plazaratu zuen, bertan zegoela. Horren arabera, laser argiaren pultsu ultralaburrek zehazki banaturiko maiztasun gailurrak sorrarazten ditu, eta maiztasun gailur horiek orrazi baten hortzak bezalakoak direnak, maiztasunak zehaztasun handiz neurtzeko erabil litezke erregela baten antzera. 1986 urtean, Alemaniara itzuli zen, Munichen Max Planck Institutuaren laser espektroskopiaren sail berria martxan jartzera. 1980ko hamarkadaren bukaera aldera, Hanschek bere orrazia egia bilakatu ahal izan zuen eta 2005 urtean Nobel saria lortu zuen. Urteetan zehar ore eta sari haunitz irabazi ditu, baina Hansch irakaslearen saririk handiena ideia berriak bereganatzearen poza izan da. Ideia, aurkikuntza, asmakizun berriak bereganatzearen poza. Niretzako, jaun-andreok, ohore handia da, Theodor Hansch, profesorearen doitasunaren aldeko grina, pasión por la precisión, passion for precision, hitzaldia aurkeztea, profesor Hansch, berorrek dauka hitza.
Good afternoon. I'm very delighted that I'm allowed to help celebrate the 10th birthday of the Dorothea International Physics Center and also celebrate the human passion for knowledge. Today I wanted to tell you about my own passion, my passion for precision. And that has to do with knowledge. How does one gain new knowledge? More than 40 years ago, when I was a graduate student at the University of Heidelberg, my professor, Christoph Schmelzer, had good advice how to gain new knowledge. He said, well, you have to look where no one has looked before. And for him, that meant building larger accelerators to look at particle collisions at higher and higher energy. And for me, it meant using lasers to make measurements that were more precise than anybody had been able to do before. I feel fortunate that the laser was invented just a few years before I started my graduate studies. We celebrate the 50th anniversary of the laser in this year because in May 1960, Ted Mayman realized the first ruby laser. The race to build the first laser was triggered actually 2 years earlier by Art Schorlow and Charlie Towns with their seminal paper on infrared and optical masers. Charlie Towns has written a book giving his perspective of these exciting years, and there he has also a passage praising precision measurements, the steady improvement in technologies that afford higher and higher precision has been a regular source of excitement and challenge during my career. In science, as in most things, whenever one looks at something more closely, new aspects almost always come into view. Of course, the exploration of light and its interaction with matter goes way back, centuries back. Sir Isaac Newton was perhaps the first to study systematically what happens if you take a beam of white sunlight and send it through a prism that disperses it into a rainbow of colors. Newton didn't know what light is. He thought the different colors correspond to different kinds of light particles. But then Thomas Young convinces the scientific community that light is a wave. If one shines light on a screen with a double slit, then at some distance you observe a striped interference pattern. And the explanation is that waves passing through the two slits can either oscillate in step, so they reinforce each other, they make bright, or they oscillate out of step, they can cancel each other, and they make dark. So from experiments of this type, Young was able to measure the wavelength of light. And what he found is that the different colors correspond to different wavelengths. Red, something like 700 nanometers. Blue or purple, something like 400 nanometers. Young didn't know yet what kind of wave light is, but of course today we know it's an electromagnetic wave, the same as radio waves or microwaves or X-rays. And if we know the speed of light, we can actually calculate the frequency, the number of wiggles per second. It's just speed of light divided by the wavelengths. And that means for visible light, say in the yellow-green, we are talking about a frequency of 500 terahertz. 500,000 billion cycles per second. And so that's, of course, much too high a frequency to be measured directly, and only in fairly recent years have we learned how to actually do that. Another very important discovery was made by looking more closely than other people had, by Josef Fraunhofer, who had engineered a spectrograph or a spectroscope with which one could look at the white light from the sun, and he discovered that it's actually not a continuous spectrum, but that there are sharp lines, the so-called Fraunhofer lines, which are due to atoms, ions, molecules in the atmosphere of the sun or in the atmosphere of the Earth. Fraunhofer didn't know how these lines come about, but chemists were quick to utilize these lines as fingerprints to identify different elements, different molecules. So spectral analysis was born long before we understood how light is absorbed or emitted by atoms or molecules. The breakthrough finally in the early 20th century came by studying the very simple spectrum of hydrogen atoms. Hydrogen is the simplest of the atoms, just a single proton nucleus and a single electron. It has a very simple visible spectrum. These Balmer lines were first actually observed in astronomical observation. And this simple Balmer spectrum proved to be the Rosetta Stone with which we succeeded to discover the very strange laws of quantum physics that govern the behavior of atoms and molecules. It inspired many path-breaking discoveries, from Balmer to Bohr, the old planetary model of the atom, the concept of wave mechanics, De Broglie, Schrödinger, relativistic quantum physics, Dirac, and the discovery of the lamp shift, the beginning of quantum field theories. And more than once, seemingly tiny discrepancies between theory and observation led to major conceptual breakthroughs, such as the fine structure that led to relativistic quantum physics and the lamp shift that led to our understanding of the importance of the vacuum, the fluctuating fields and virtual particles in the vacuum that determine the precise properties of atomic energy levels. I had the good fortune to join the group of Art Schawlow at Stanford University in 1970 as a postdoc. Art had a good sense of humor. Here he is shown with a toy ruby laser, and he shoots a blue Mickey Mouse balloon inside a clear outer balloon that stays unharmed. And that was his favorite lecture demonstration. If one met him in the hallway of the Varian Physics building at Stanford, he would ask his students, "What have you discovered?" And for many, that was actually an important message. They really were made to think, wow, I'm not here to learn something old. I'm here to discover something new. And of course, sometimes one was embarrassed because one just hadn't discovered anything new. But after 6 months or so, I could actually proudly tell him that I had discovered something new. I had played with a pulse dye laser. Dye lasers were these wonderful, widely tunable lasers that had been invented 4 years earlier. And here's a picture of a nitrogen-pumped pulse dye laser, a liquid dye cell pumped by ultraviolet flashes from a nitrogen laser. And the resonator is made by one partly transmitting mirror to the left and a diffraction grating to the right. And by changing the angle of the grating, you could change the color of the laser from red to yellow to green. It was spectacular, but the spectrum was rather broad, so it wasn't really useful for any kind of serious spectroscopy. But what I had discovered is I had wondered, gee, the laser beam at the side of the grating is very tiny. We don't illuminate very many grating lines. What would happen if I expanded the beam? And I happened to carry a little pocket telescope in my trousers, which I used to read the slides at lectures from the back row. So I quickly mounted this telescope to expand the beam, and it made a tremendous improvement. And with a little more engineering, could I make a dye laser that was not only widely tunable, but as monochromatic as some of the gas lasers that people had used for new types of nonlinear high-resolution spectroscopy. So this simple recipe spread very quickly. Very quickly, hundreds of laboratories operated lasers like this. And in 1973, I was delighted to share the award California Scientist of the Year with Art Schorlow, given by the California Museum of Science and Industry. At the same ceremony, there were also 2 industrialists of the year honored, the founders of the company, Hewlett-Packard. So that certainly supported my career at Stanford. I didn't go home to Germany as I intended, but I signed on to become a professor at Stanford University. And I utilized this highly monochromatic tunable dye laser to look at the red Balmer alpha line of hydrogen by a technique called saturation spectroscopy, which gets rid of the Doppler broadening due to the rapid thermal motion of the atoms. You have 2 counter-propagating beams, and you get a signal only if the 2 beams interact with the same atoms. And these can only be atoms that are either standing still or at most moving sideways. And so very quickly, we were able to, for the first time, resolve theoretically predicted fine structure components underneath the Doppler broadened line that classical spectroscopy saw. And in particular, we saw the lamp shift, the splitting between the 2s state and the 2p state plainly resolved in the optical spectrum. This was the beginning of a long adventure aimed at ever higher resolution and ever higher measurement precision in the simple hydrogen atom, with the idea that if we look closely enough, maybe we will one day again find a surprise, something that might advance our understanding of microscopic physics. Have we seen the surprise? Well, at least we have arrived at some kind of puzzle that I will tell you later on. But here is a record of improvements over the years. So classical spectroscopists were glad that they could measure the wavelengths of spectral lines to 6 or 7 decimal digits. And then came lasers and methods of Doppler-free spectroscopy. And by the late 80s, it was possible to measure wavelengths to something like 10 digits. But then classical wavelengths measurements ran out of steam, because you always have to struggle with distortions of optical wavefronts. And the fact that there has been progress beyond that has to do with the fact that we have learned to measure the frequency of light rather than the wavelength. We are at a point where we are almost now limited by how well we know our unit of time per second, but the same techniques that make it possible to measure the frequency of light make it possible to construct new optical atomic clocks, and I will tell you about some progress later on. So in order to measure hydrogen frequencies to 14 digits or so, of course we need a sharp line. The Balmer lines are not so very sharp, but there is one resonance in particular that's enormously sharp. It's a 2-photon resonance between the ground state and the metastable 2s state that one can excite with ultraviolet light at 243 nanometers. And the natural line width of that transition, limited by the lifetime, is on the order of 1 hertz, whereas the optical frequency is on the order of 10 to the 15 hertz. If you take 2 laser beams coming from opposite directions, the first-order Doppler shifts cancel, and you can excite this resonance free of Doppler broadening without the need to select slow atoms. And here is a resonance, a typical resonance. It's not our best one. And we see we are not yet at the 1 hertz. We have a few hundred hertz line width, partly limited by the short time the atoms spend in the light field. But there's also some second-order Doppler broadening. Nonetheless, it's a sharp line. If we would take the visible Balmer spectrum that we had looked at in the beginning and would stretch it so that it fits on the same scale, we could wrap it around the equator. And not only once, but about 20,000 times at this scale here. And to do justice to such a sharp resonance, Art Schorlow, of course, had a word of wisdom. He said, whenever you want to measure anything precisely, never measure anything but frequency. And the reason being is measuring a frequency, counting the number of cycles per second, is intrinsically a digital procedure. It's immune to many kinds of noise. But as I said, it was almost impossible to measure the frequency of light. Not totally, so we spent a long time. Finally, in the end of the 90s, we had made some absolute frequency measurement of this sharp 1s, 2s transition to something like 13 digits. At that time, that was the most accurate measurement of an ultraviolet or visible optical frequency that had ever been made. From the frequency, we could derive the Rydberg constant from this frequency and from the frequency of other resonances in hydrogen, I should say. We could determine the lamp shift of the ground state, which at the time was perhaps the most accurate test of quantum electrodynamics for a stable atom. And if we believe in quantum electrodynamics, then from spectroscopy of hydrogen, we could determine the charge radius of the proton, the finite size of the proton, and by making similar measurements in deuterium, also the so-called structure radius of the deuteron. I said it took a tremendous effort. It took our effort and the effort of other people. We took advantage of a so-called harmonic laser frequency chain that had been constructed at the German National Metrology Lab, the Physikalisch-Technische Bundesanstalt in Braunschweig. The Braunschweig team in 1996 published a paper on the first phase-coherent frequency measurement of visible radiation. They had set up a frequency chain that occupied 3 large laboratories in 2 separate buildings. And the whole chain with many lasers and oscillators and electronic feedback circuits was designed to measure just one particular optical frequency, the red calcium intercombination line that had been proposed as a secondary standard for the unit of length. And I could explain how it worked, but I don't have to, because these frequency chains have all disappeared. There have been maybe a handful of laboratories in the world that had built up these complex chains, and they all have dismantled them. They all have plenty of free laboratory space and teams eager to do something different. And the breakthrough came about 10 years ago. It was celebrated by a number of newspapers and magazines, and that is the invention of the optical frequency comb. The frequency comb is a remarkably simple tool that makes it actually possible to measure the frequency of light. It can, in a single step, provide a phase-coherent link between the optical and the radio frequency region, and it can be used as a clockwork mechanism for an optical atomic clock. In my Nobel lecture, I have written my perspective of how this idea came about. But as I say, it's in hindsight remarkably simple. At the heart of a frequency comb is a so-called mode-locked laser, a femtosecond laser. As any laser, it has an optical resonator, 2 mirrors, and there is a short flash of light, a short light pulse, bouncing back and forth. So this is similar to the Gedanken light clock of Einstein, except it's a laser, so we have an amplifying medium, and we can keep it going even though we couple out a train of light pulses. So this by itself is nothing new. Such mode-locked lasers have been perfected over decades. They have been used in the ultrafast community as flashlights, as sources of short light pulses to study fast phenomena in chemistry, dissociation reactions, in solids. And so why do we call it a frequency comb? The people interested in precision measurements, they typically use a different kind of laser, also 2 mirrors, But rather than a pulse of light bouncing back and forth, they make sure that a single standing wave is excited, a single mode of the electromagnetic field. So we generate a nice sinusoidal electromagnetic wave and have one single frequency. The frequency is determined by the condition that an integer number of half wavelengths has to fit between the two mirrors. Now, the laser builders know that it's typically not trivial to make a laser go in a single frequency. More likely than not, it wants to work in two modes. So now we have two frequencies, two different wavelengths. And of course, I need to look at the superposition. So the two waves of different frequency interfere like two tuning forks, and out comes a pearl string of very elongated wave packets. So where the waves are in step, they make bright. Where they're out of step, they make dark. If you have three modes, the wave packets can be shorter. And just 5 modes are enough, as in this animation, to make short flashes of light separated by a remarkably long time of dark. The modes are on all the time, but during the dark period, they cancel each other through interference. So this is outside the laser. Inside, we see that we have a pulse of light bouncing back and forth. Every time it's at the mirror, it looks complicated because there is interference between forward and backward running wave, a standing wave. So that's another way of looking at our mode-locked laser. In the spectral domain, it oscillates on a whole comb of frequencies. And the spacing between adjacent lines is just precisely equal to the pulse repetition rate. If that is satisfied, then things work as nicely as in this animation. But how do you make sure in a real laser the spacings are precisely equal? Well, there are many effects that would tend to counteract the dispersion in the laser medium, in the mirrors. But fortunately, the ultra-fast laser community has found tricks to make sure a laser runs stably in this mode-locked fashion. They rely on things like saturable absorbers, Kerr lens effects that make it in the survival interest of the modes to play together in an orchestra and make intense short pulses, because these intense short pulses can slip through the saturable absorber without suffering high losses. But any mode that doesn't like to play in the orchestra, that wants to oscillate at its own frequency or with its own phase, will suffer losses and will quickly be extinguished. So it's a process of nonlinear self-organization that assures that we have a perfectly evenly spaced spectrum of lines. Here is a computer animation of a mechanical frequency comb that one could actually construct and build. It's 10 pendulums that have been trimmed so that the first one makes 30 oscillations per minute, the next one 31, the next one 32, the last one, in this example, 39. So if I let them go, they quickly get out of phase. Each pendulum corresponds to one of the modes of the laser, to one of the comb lines. And we see that after a while they seem to oscillate with random phases. Certainly the oscillations cancel each other. If one looks more closely, we see it's not totally random. There are patterns emerging. So with some training, one could learn to read time from such a pendulum array. Now half a minute has gone by, so one could use it as an egg timer, for instance, or one could put it into one's office for meditation, or you could make big ones as outdoor art. And so if we wait long enough, eventually they'll all be in phase again, and that is when in the mode-locked laser the next light pulse would be emitted. So now that is so, and then it continues. So that's the mechanical frequency comb. So these principles are very simple. They can be understood by any beginning student. nonetheless, most experts were totally surprised that this would work. And in particular, they were surprised by how far these principles could be carried. Here is an octave-spanning optical frequency comb produced by taking a mode-locked titanium sapphire laser, which you can buy, a laser that makes pulses of maybe 30 femtosecond length at a repetition frequency of a few hundred megahertz, deep red light. You take this light, focus it into a special microstructured silica fiber with a small solid fiber core, just a few microns in diameter, surrounded by air-filled holes. And by focusing the light so tightly and guiding it by total internal reflection, you can take advantage of the fact that the refractive index of the quartz itself changes with intensity. And as a result, you have a process called self-phase modulation. And the spectrum of the light pulses becomes broad. Instead of deep red light, you get white light out at the other end, white light that you can disperse again into a rainbow of colors. I oversimplified what is happening in the fiber. There are many complicating nonlinear effects. But nonetheless, complicated as it may be, the processes are so reproducible that successive pulses are correlated in their phases, and you still get a comb. So I have what looks like white light, but really I have 1 million sharp comb lines, and still very precisely separated by the repetition frequency of the laser that I can count very precisely, because it's in the radio frequency or microwave regime where I can buy precise counters. There is one little problem that I didn't point out so far. I know the spacing of the comb lines very precisely, but I don't know where the comb lines are. If I could be sure that successive pulses look identical, then the Fourier analysis of such a periodic function would give me comb lines that are precise integer multiples of the repetition frequency. But the mode locking mechanism allows for a phase slip from pulse to pulse, and this phase slippage translates into some shift, some carrier envelope offset frequency. And in general, this frequency is unknown. But if you have such a broad comb that spans more than an octave, you can easily measure this slippage frequency by taking light from the red end of the comb, sending it through a nonlinear crystal, produces the second harmonic. So you have new comb lines which are now shifted by twice this unknown carrier envelope offset frequency. And by looking at a collective beat node, new frequency doubled blue comb, original blue comb lines, you get a radio frequency beat node that tells you what that offset frequency is. And if you can measure it, you can use servo controls to make it go away. So you can indeed have this ideal situation where successive pulses have the same electric field, the same waveform, and where I can be sure that each comb line is at a precise harmonic of the pulse repetition frequency. And I can use this comb in two different ways. I can measure the repetition frequency with a cesium atomic clock, and then I know the absolute frequency of each and every comb line with the precision of my cesium clock. Or in the future, to build an optical clock, I can take a very sharp optical resonance. I can take a nearby comb line and use electronic servo controls to lock it to this sharp optical pendulum, and then the repetition frequency of my laser becomes a known integer fraction of the optical frequency. So to use this comb to measure some unknown laser frequency, what we do is we take the pulse strain and my unknown wave and superimpose them with a beam splitter, and a detector will record a low frequency beat node whenever my unknown frequency comes close to a comb line. So if I know my frequency approximately, so that there is no doubt as to which comb line I'm near to, then this beat frequency tells me precisely where I am. Roy Glauber is not happy with this explanation. He says, where are the photons? And of course he is right. I think it's an interesting question, but we have no time to discuss this. So just to summarize, our femtosecond laser frequency comb, it's a simple laser that acts as if we had 100,000 or 1,000,000 ultra-stable lasers operating at once. It has become a revolutionary optical wave meter. It allows us to count frequencies now from DC to the ultraviolet, not directly, but taking advantage of nonlinear optical phenomena such as difference frequency generation or some frequency generation. I mentioned clockwork for optical clocks. It's an optical frequency synthesizer. If I have a known reference frequency somewhere, I can synthesize new reference frequencies anywhere I like. It has also been applied as an ultra-stable microwave source. For us, it's a wonderful enabling tool for fundamental measurements. In the ultrafast community, it's interesting to have a source of phase-stabilized femtosecond pulses. And to my colleague Ferenc Krauss in Garching, it has become a key to new adventures in attosecond physics. I mentioned a frequency comb based on a titanium sapphire laser. This is now a museum piece. The frequency comb was handed to the Technical Museum, the Deutsche Museum in Munich about 2 years ago. Modern frequency combs are based on fiber laser technology. Here is a commercial comb, including also servo electronics that you can buy from a spin-off company operated by 2 of my former students. And these combs are now used in many laboratories around the world. All the national metrology labs have these combs, but more and more laboratories discover other uses. And right now, the little company, I think, ships 1 such comb every 2 weeks. And the reason, of course, is that there is an evolutionary tree of applications that go way beyond the original purpose. I've told you about this self-reference octave-spanning frequency comb. And the original purpose was to measure the frequency of light. But if you can measure the frequency of light, you can also measure distances. You can make optical clocks. You can test fundamental physics laws. I will talk about some of the other applications as we go on. But let's start with frequency measurements. So the original purpose for us was to measure the frequency of the sharp hydrogen 1s, 2s transition. And here is a sketch on the poster put out on the occasion of the Nobel Prize that explains how you use a frequency comb to measure the frequency of a hydrogen line. So you have a tunable laser. You send part of the light to the hydrogen atoms and see whether they get excited. And if so, then you send another part of the laser beam to the frequency comb to find out just what is this frequency that the hydrogen atoms find exciting. In reality, it looks a little bit more complicated. This is a photograph of our hydrogen spectrometer that has evolved now for more than 20 years, here with Nikolai Kolachevsky and Mike Fisher, adjusting a dye laser system that was used in the old days. There is a hydrogen atomic beam vacuum apparatus in the foreground. Of course, to make optical frequency measurements, we need a reference. And one good reference, one very good reference, is a transportable cesium fountain clock built in Paris, at the Observatoire in Paris. It's the world's most accurate transportable cesium fountain clock. So the clock observes microwave transition in the ground state of cesium, a hyperfine transition. And in order to have a long observation time, you cool the atoms. You have slow atoms that you throw up by light, and they fall up. So that they go up and eventually fall back down to the microwave cavity. And in this way, one can get very sharp resonances. Here is Michel Abgral from Paris adjusting some diode lasers for laser cooling of cesium. Where I should mention that the idea of laser cooling, which we came up with Art Schorlo back in 74, was also meant to improve precision spectroscopy of hydrogen. So far, it's very difficult to laser cool hydrogen atoms. So we made measurements of this transition frequency with a comb. The very first absolute frequency measurement with a laser comb, not yet the elegant octave spanning one, was made in the summer of 1999. And we were proud that we could reach an uncertainty of 1.9 times 10 to the minus 14. There is a later measurement listed here from February 2003 where we did use the elegant comb and we confirmed the earlier measurement. We didn't make an enormous amount of progress as we had hoped. Nonetheless, we have two measurements differing by a few years that agree within their error limits. And one would say, well, that's what you expect. But some people were disappointed. There's a theorist, Harald Fritsch, at our university and at CERN, who had called every day during the February 2003 campaign to get a preliminary measurement because he had predicted that we would see a drift based on some suspected drifts of the electromagnetic fine structure constant that astronomers had speculated about. And Fritsch had argued that if you believe in grand unification of all the fundamental forces, then if the electromagnetic fine structure constant drift, the constant governing strong interactions and thus the magnetic moment of the nucleus should drift even more, and he had predicted some amplification effect that should have become evident. So far there is no evidence for changing fundamental constants. Nonetheless, we are still at it. Here is our recent team in the spring of this year working on a new, much improved measurement of this hydrogen frequency. We have a first round of data already in the computer. We are hoping to make another round later in November where we will use an optical fiber link to compare our hydrogen frequency directly with a primary cesium atomic clock in Braunschweig. So it's a fiber link that's already operating using existing fibers for communications that can be used to disseminate optical frequency standards thanks to the frequency comb technology. But one can argue, why do you want to measure this frequency so well? Well, one thing I can derive from the hydrogen frequency is the Rydberg constant, which is a very important fundamental constant. But if I look up on the internet, what is the value of the Rydberg constant? I find that the most recent data, according to CODATA, have an uncertainty of 6 times 10 to the minus 12. So what is this? Only 12 digits, and we measure hydrogen to 14 digits. Well, the problem is, if I want to derive the Rydberg constant by comparing the measured hydrogen frequency with theory, I need to worry about corrections due to the finite size of the proton, the root mean squared charge radius of the proton. And this, even though the proton is a very important, there are only two stable hadrons in the universe. The proton is one of them, the neutron the other. But we don't know its charge radius very well. And what is worse is that the charge radius has been determined by hydrogen spectroscopy. So if I want to test 3D, I am certainly not in a good shape. And it would be wonderful if one had an independent way of measuring the size of the proton. And for 12 years or so, we have been partners of an international collaboration that has pursued just this goal, to measure how small is a proton. And in the last summer, there was a breakthrough, as you can see, from the excited gestures of some of the team members, because that summer we succeeded at the Paul Scherrer Institute in Switzerland, which has a strong muon beam, to look at muonic hydrogen atoms, man-made artificial atoms, where the electron is replaced by a 200 times heavier muon. The muon is not a stable particle. It has to be freshly made, and it decays within microseconds. But it lives long enough that one can make atoms and one can do spectroscopy. of these atoms. And since it's 200 times heavier, it comes much closer to the proton, and therefore its energy levels are much more sensitive to the size of the proton. So as I said, it's an international collaboration with, I think, 32 participants now from 12 different institutes. The spokesmen are Randolph Pohl from our laboratory and Franz Kottmann from the ETH. The atoms are made by taking muons and shooting them into a gas target of molecular hydrogen, and you create muonic atoms in high Rydberg states, somewhere in 14, and most of them decay promptly and very quickly to the ground state, emitting 2 kilo-electron-volt X-rays, and they're gone. But maybe 1% decays into the metastable state, which lives longer. And this metastable 2s state then serves as a start for laser spectroscopy. So in ordinary hydrogen, the 2s state is less tightly bound than the neighboring 2p state because of vacuum fluctuations of the electromagnetic field. In muonic hydrogen, it is more tightly bound because of vacuum polarization. In the s state, the electron can actually pass right through the proton, and it dives through a shielding cloud of virtual electron-positron pairs. And the transition energy can be provided by an infrared laser at 6 microns. So if you wait long enough till all the other levels have decayed, then you take your laser, you illuminate your target, and if you're lucky, if there is a resonance, you again observe a 2 kilo-electron-volt X-ray photon. The laser system provided a major challenge because of the short lifetime of the muon. Once you get a trigger signal that tells you, get ready to fire the laser, you only have a few hundred nanoseconds to do so. At the same time, you need substantial energy to, in the end, produce 6 micron radiation, which in our case was done by several stages of coherent Raman scattering in molecular hydrogen. This 6 micron radiation is then sent into a multipass cavity to excite the muonic atoms. And the experiment here is sketched. You have muons coming. You need a trigger signal, which is provided by thin carbon foils that emit secondary electrons. So some scintillation detectors tell you, okay, now get ready to fire the laser. And then you do that and see whether you get the signal. In the experiment, the laser fires about 500 times each second. But on resonance, the expected signal is only about 6 events per hour. So one has to get rid of lots of unwanted background signals before one has a useful signal. Here is an animation that shows this apparatus. So you see a cyclotron trap. You first produce pions, pi mesons, by slamming fast protons into a graphite target. These pions are injected into a magnetic trap where they decay into muons. The muons are magnetically captured and slowed down, and it eventually sent through a vacuum pipe guided by magnetic field coils into the target chamber. And so here is the animation that shows. So see, I was so excited when the experiment had worked that I couldn't resist making this animation on my Mac computer. So here is a muon magnetically guided and slowed down by passing through a degrader foil, and then a high voltage pulse sends the muon on its way. And this curved path serves to get rid of a lot of unwanted background particles. So here's a target chamber. Okay, here is a secondary electron, so scintillation signal. There's another stack. And here is the hydrogen cell. The muon forms an atom, and here comes the laser and gives a signal on an avalanche photodiode. So during the experiment, there was some online data processing because we knew what laser frequency corresponds to which proton radius, and one could watch what happens. And if the co-data accepted value of the proton size was right, it should be where the upper error bars are. Earlier electron scattering experiments at accelerators had given a somewhat lower value with bigger error bars. And so I think there were 3 months of beam time in the summer of 2009, and 3 days were left when the situation looked like this. Nothing in the range of interest. And Randolph Pohl then said, oh, what the heck, let's be crazy and look at some other frequencies. And that was a very good thought, because the resonance is somewhere else. Translated, okay, here's the resonance. Translated into the proton radius, here is the accepted co-data value, and this is the proton radius derived from the ionic hydrogen experiment. From the proton radius, of course, we can also improve the Rydberg constant. Here's a history of measurements of the Rydberg constant in our group, but also in Paris and the group of François Pirapin, who, by the way, was an important participant in the ionic hydrogen experiment. And again, we have the accepted co-data value, and the Rydberg constant would have to shift by something like 5-fold standard deviations. Now it would be much more accurate, but clearly we have a problem. And this problem has been sketched by a cartoonist of the New York Times. The article that appeared in July of this year made it on the cover of Nature, and just the most recent issue of Scientific American has some feature which sums up in the end, whatever the answer, physicists will most likely have plenty to keep scratching their heads about for years to come. So it's a puzzle, and we don't know what is the solution. It's very unlikely that it's an experimental error in the ionic hydrogen experiment, because that has been planned for more than a decade. It could be errors in the quantum electrodynamic calculations. It could be some unrecognized line shifts in hydrogen spectroscopy, but not in the 1s/2s shift. That's 2s frequency. That is quite unthinkable. So we have to be patient. We have to see what comes of it. But at least, I think the subtitle is New Findings Challenge a Basic Theory of Physics that presumably had been settled. So maybe it hasn't been settled. Okay, so let's go back to our frequency comb applications. I mentioned optical clocks, and I will briefly say something about that. Clocks, of course, are very important in science and technology. They have evolved over centuries or millennia. And major progress has often been made by going to a faster pendulum, from the 1 Hertz pendulum of a grandfather clock to the ultrasonic quartz tuning fork in my quartz watch to the microwave frequency of a cesium atomic clock. And now we are talking about optical pendulums, ions, atoms oscillating with the frequency of light, 100,000 times faster than the cesium atoms. And there are different approaches. People use ions in ion traps, a single ion suspended in vacuum in free space. Other people like neutral atoms. Of these you can use many. You can use 100,000 or 1 million to keep them from colliding. You can make an array of laser tweezers, a so-called optical lattice. Molecules might be interesting. And here is summarized the progress. So cesium clocks have advanced over the decades to now reach an uncertainty of a few times 10 to the minus 16. Optical clocks have a much shorter history, but they have advanced and are still advancing much more rapidly. And I think just last month in Science there was an article by the group of Dave Vineland comparing 2 aluminum ion clocks these aluminum clocks have a proven reproducibility of something like 3 times 10 to the minus 17. And they have observed a gravitational redshift by moving one something like, I think, 30 centimeters higher than the other. And they show that indeed Einstein is right. If you step up a ladder, one rung is enough to make you age faster. But it's only a few attoseconds per second or a few nanoseconds per lifetime. But nonetheless, it's an observable effect that you can observe with these very precise clocks. So, of course, tests of relativity is only one of the applications. There's a whole list of other applications, but I see my time is running short. So I will very quickly touch one more topic, the calibration of astronomical spectrographs. There is a new generation of astronomical telescopes with large light gathering power on the drawing board. And there, astronomers hope to use very accurately calibrated spectrographs to search for Earth-like planets, to test for general relativity, to address this question if fundamental constants are constant. One can also study primordial nucleosynthesis. In October of 2009, there were some headlines on CNN that 32 planets have been observed outside the solar system at a telescope of the European Southern Observatory at La Silla, Chile, using the HARPS spectrograph, a high-accuracy radial velocity planet searcher. And the idea is that you look for a tiny wobble of the star that is imported by an orbiting planet. And this can be observed by looking at tiny periodic Doppler shifts of spectral lines. All planets that have been discovered in this way here are big Jupiter-like planets. And to look for small Earth-like planets, one would have to have substantial better calibration of the spectrographs. And so to see how well frequency combs and astronomical observatories can work together, we actually worked with the Vacuum Tower Telescope in Tenerife, and we implemented an astrocomb, an optical frequency comb, with a spacing wide enough that the astronomical spectrograph can resolve it. So a typical fiber comb has 250 megahertz, which is too fine to be resolved. But you can filter this comb. You can suppress most of the comb lines and take only every 10th or every 50th comb line. And then you have, here is our team, Thilo Steinmetz and Constanza Arroyo-Haug, implementing this comb. And then you have a nice ruler-like set of calibration lines, here superimposed on some Fraunhofer lines. And we actually published this work in Science, but we thought, well, this will not be of interest to anybody because for sure the Fraunhofer line and the solar spectrum have been measured with high accuracy. But we got phone calls from researchers who said, we are studying or we are doing three-dimensional modeling of the solar atmosphere and we cannot find well-calibrated spectra. Can we use your data? And now the Solar Observatory has ordered an astrocomb from our little spin-off company. One final thought, what one might do with a comb. We know that the space between galaxies is filled with intergalactic hydrogen clouds. How do we know? If we look at light from distant quasars, we see a forest of absorption lines. And this is actually one and the same line. It's a Lyman alpha line of atomic hydrogen, but with different Hubble shifts because of different distances of these clouds. And so the idea is if we look at this forest with very high precision today and maybe 10 years later, maybe we will see some changes in the redshifts that would be a telltale signal for the continuing expansion of space in the universe. So maybe some more words of Charlie Towns are good to conclude. He writes, there is much that we don't understand. In many cases, we don't understand that we don't. And the really surprising discoveries will probably depend primarily on individuals, not teams or committees, although the individual may be part of a team. So with this praise of curiosity-driven research, we have reached the end.